Our third stopover is about measuring techniques, and the experts there are Tom DeMille, Giulia Resent, and Jan van den Bulcke, and a tiny bit also myself. So please, Giulia, take the screen. And unmute yourself if you didn't unmute already.
Hello crew, the QNAP train has now arrived at Measuring Techniques talk. The survey on board had a nice script and we collected many questions.
Giulia, you're muted. You're muted, Giulia.
So hello crew, the QNAP train has now arrived at the Measuring Techniques talk, and the survey on board had a nice script and we collected many questions. So now I will give the word to Tom and he will give us a nice overview on techniques.
Thank you, Giulia. So I received some questions about the catering on the train. I will not be able to answer them. So I received some general questions about measuring techniques in wood anatomy. And now before I get hate mail, I just want to give a small overview. It's not complete at all. I'm just talking a bit from my expertise. So a lot of has been said already in the previous stops. Depends on what you want to discover, like Lenka said. And so many things depend on the surface preparation. There's a plethora of different software routines, open source, free, or with a license, going from, so I'm talking here, just going from you have seen now the sample preparation. And the next stop with Jesper, you will also see the data analysis. And here we're just going to quickly give a small overview on the measuring technique. So here you see a polyalthia sample. It's from the understory tree from the Congo Basin. And basically what you want to have is you want to annotate wood anatomical features. You saw the triangle from Lenka. You want to have vessels, you want to have parenchyma, you want to have fibers, the three broad anatomical traits. So on the left, you see the vessels, then you see the parenchyma in this case of the Annonacea, and the right, you see the fibers. And if you want to go a step further, you want to measure the fiber lumina thickness or the fiber wall thickness. The next slide, Giulia. So I gave a small overview here. So either you have microsections, either you have sanded cores, you have microtome cores, or you have embedded cores, as being said lastly, but you also have raw cores. I call them raw cores, just as I see Holger is standing in the forest now. I'm a bit distracted, so he's taking cores. So if you have the raw cores, there are also possibilities. And there is even splinters, shavings, or small pieces of wood. If you look at a very high detailed wood anatomy, you would go to scanning electron microscopy maybe to see perforated pits. All of that together. So there's a general workflow here, going from light microscopy, fluorescence microscopy. Maybe for early wood vessels on some species, you will go for a flatbed scanner even, or you want to go for blue intensity. Then there is X-ray CT. I will elaborate a bit further on that. Or there is, as Emanuele said, a confocal laser scanning microscopy. Now, not everybody has a CLSM or has this XCT device, certainly not, but there are some reference institutions and you can just reach out within the QNet network on very specific questions. There's also a research page on the QNet website. Okay, so I put the 3 dots here. There are also other techniques. Same thing for the next step being, so you get this, so you got your samples, you get them out of a tree, you take an image of that. And now this software like Roxas, Fiji, this will then this will allow you to annotate features on your images to export them into a data frame, CSV or Excel. Is that area, tangential diameter, and so on. So I give you a general overview of Roxas, which is free, but you need the Image Pro, and then you have Fiji, which is free, and there's also several plugins you can use for Fiji. There is WinCell. I'm not gonna mention them all. There are many different measuring softwares. Also, every microscope have it, like Nikon or Olympus have their own measuring software. So that is mostly, it's all very generic. It's almost the same thing as they use in the medical sciences. And then you would eventually go for the data analysis. But since you can go to the next slide, Giulia. Since a lot has been talked about surface preparation, what if, and that's what bit of my expertise is, not a sales pitch, but what if you don't need or don't want to do sample preparation? What if you just start with the raw cores and you don't have, you don't want to do the tedious sectioning? Then there still is X-ray micro CT. So on the top view, that's the typical thing what people see when they think about 3D scanning. This is a 3D rendering of a increment core, so of a tree core taken from a tree. But that's actually mostly what we don't see, because that's just a visualization. The most thing what we see is on the bottom. It's just a stack of images. So this is a bristle combined core. On the left, you see that it's in a paper straw. I cheated that they have already been sanded, but I scanned them anyhow. And the main advantage of CT is that you can pick your own slice, free from defects, free from surface preparation actually, or ruptured cell walls. And that is for me the main advantage of a CT. Once you extracted the proper slice or a few slices, here you see one for bristlecone in the first pane, then birch, then oak, and then beech. Then you can just export them to standard image analysis software as you would treat CLSM images or anything else. But I think it's now up to Jan. I think you can also stay in the 3D image itself, right, Jan? So I'll let you talk about the actual 3D analysis on 3D images. Yeah.
Yes, thanks, Tom. So when it comes to 3D image analysis, visualization, and modeling, I must say that CT scanning is certainly not the only technique capable of delivering 3D imagery. The confocal laser microscopes are capable of doing that as well. To some extent, the scanning electron microscope, whether or not combined with, for instance, field ion beam milling, can do that as well. But indeed, X-ray CT scanning is very much known to produce actually 3D volume data sets. Now, when it comes to 3D image analysis, I must stress that in certain parts, you can use standard algorithms that have been developed for two-dimensional image analysis. But for most of the image analysis algorithms that you want to use, they have to be tailored to the third dimension. So it's not always as easy for just taking a algorithm suited for 2D analysis and just using it on a 3D data set. Then secondly, something that indeed has been mentioned by Tom as well, when it comes to software, there's many flavors. You have to consider whether you want to go for open source or freeware, or you have some budget available, whether you want to have a graphical user interface, or you're doing everything code line based. Certainly the paid versions, I'll show some options. Of course, not only have a GUI, so graphical user interface, but they're often also offer the opportunity of some kind of scripting engine where you can write your own scripts, or even a full binder to Python. You also have to think about, am I dealing with surface or point clouds, or is this really volumetric data that I'm dealing with, such as the data that's coming out of CT scanner? There is a true difference, especially if you want to do a 3D visualization and the kind of package that you're going to use. You have to be aware of the fact whether you're dealing with a surface or whether you're dealing with a volume that you want to visualize. And then, as mentioned by Tom as well, the same here actually, any kind of equipment that is capable of, so CT scanner, CLSM, SAM with FIPS or FIP-SAM, any kind of machine that is capable of producing a 3D imagery. Most of the times, these vendors, these companies offer their own product for analysis, visualization, and in some cases, but hardly ever, also for some modeling. So this is certainly not a full list of all software packages available, of all literature available on these particular questions that we got on the 3D story. Next slide, please, Giulia. Just to give you a few ideas, Tom mentioned that for him, and for instance, for the bristlecone topic, it's very important that you can acquire a 3D data set, but it's not always necessary to do 3D analysis with a 3D data set. It might be as interesting to be able to select the proper slice, and then work into the starting from the 3D data set, but moving to a 2D and to a 2D image analysis tool chain. Now, when it comes to 3D image analysis, I think most of you and many of you are also involved in ecophysiological studies regarding cavitation, embolism, and embolism repair. That's a community that's actually also very much working towards quantitative wood anatomy, focusing on vessels. And I just took two examples here, like what you see at the left-hand side is a branch of a certain wood species. And at the right-hand side, you see that same branch after a certain amount of time where you have embolism formation. So all these black dots that you see, these are actually cavitated vessels, right? And the idea behind using X-ray CT scanning is that you can do this in a non-destructive way. So you don't have to cut, you don't have to prepare the sample. And secondly, you can follow the dynamics and function of time of this particular kind of phenomenon occurring. And I'm just mentioning a couple of famous names. I'm forgetting many of them, like Brandon Choate, Sylvain Dalzon, Cathy Steppe, and many others, Steven Janssen, but also Ute. I just see Ute on my screen, so Ute as well, she's also involved. And many of you are also involved in this ecophysiological research, where quantitative data, and especially also like the vessel networks in 3D, are of interest to these people. Next slide, please, Giulia. But also for us as a community, and I think some people referred to the or expressed their interest in the first poll or the second poll on wood technology. Also here you can actually exploit the true 3D nature of the data sets that you can capture. So at the left-hand side, you see vessel mapping again. On the top left-hand side, you see vessel mapping on a tropical wood species. And then at the bottom side, it's actually a plug, a 3-centimeter plug of oak, and the 3D network of the early wood vessels was of interest. Then the picture labeled with a C, that was actually a hybrid aspen sample, and they were interested in measuring fiber lengths in a non-destructive way. And that's where you need this 3D data set. That's where you need 3D image analysis, but also in wood for wood technological purposes, for instance, and not referring to the dynamic process, such as with embolisms, but in this case also X-ray CT scanning can be very beneficial. And I write that before after, because you can take the same sample, you scan it at a very high resolution, and then you're going to subject that same sample to any kind of wood treatment. In this case, they were interested in a certain chemical modification and how it impacted not only if there were certain vessels blocked or filled, like bulking of the material, which is a typical wood treatment, but also whether or not it impacted cell wall dimensions. So, and then instead of measuring 100 samples, you could compare the same sample before and after. So this is actually an intricate feature of CT, and that's why you really can adhere to the 3D data set and the 3D image analysis as well. Next slide, please, Giulia. Just referring a bit to also what was talked about when talking about confocal laser scanning microscopy, but also the slide scanner that was referred to. So you don't need to stick to a single field of view of your sample or a single object. You can also scan that particular object in 3D in different steps. So you take different volumes, you stitch them together, and then you can slice through them in any kind of direction that you want. Well, Tom was mentioning, like, I want to select my slice. So what you see here is resolving anatomical details. These are 10 or 11 volumes, I don't remember, that we have been stitching together and then slicing in a virtual way in any direction that we want. So it's also possible to capture time series. We know that there is not yet an entire workflow available to my knowledge, but there's ongoing work by several groups to make this possible. Next slide, please, Giulia. So, and then there were also specific questions on what kind of software packages are there and what kind of software package can I use? And there's, as I said, many different kinds of flavors, depending on what your requests are, what your budget is as well. So I listed them as like the top ones are free, fully free, and there's a graphical user interface. Like the middle ones, you have to pay for them, but they come, of course, with the benefit of being highly efficient They also come with a graphical user interface with some analysis toolbox available with a scripting engine. So we also use all of them here at our laboratory. And if you want to stick to pure coding, of course, then I don't have to tell you about Python, MATLAB, Mathematica. These are very efficient toolboxes as well. But if there's more questions, you can ask them in the chat, of course, or you can contact us later on. And I have one final slide. If you could go to the next one. Yes, thank you very much. I'm not going to go into detail on surface and point cloud rendering, because for that you have different packages, and it is most of the time less of an interest for in terms of quantitative wood anatomy and 3D data gathering, because we're talking about volume data, not surface data. And then we had a very specific question on the 3D modeling, actually, the biomechanical modeling from a nanoscale to a micro scale. That's a very hard question to answer. I don't think, but I'm not a biomechanical engineer, so I cannot say for sure, but I don't think there is a dedicated package to do that. Many people use different packages, but what I have been working with in collaboration with some, especially the civil engineers that I have been working with, that I've been collaborating with, is Abacus, which is a very famous finite element program, can do both volume as well as surface finite element modeling. There's COMSOL Multiphysics, that's also a very well-known package for doing but mechanical modeling in general, and ANSYS. So that are the three most common ones. I am not aware of any free software packages that can really live up to what these commercial packages give in terms of performance, speed, and capabilities. And that's about it. Up to you, Giulia. Oh, sorry, Georg. My apologies.
That's very fine. Thank you very much, Jan. I think that was pretty cool. I guess everyone agrees with me, and very modern. Now, when we turn to two specific questions about Roxas, this is something I started developing roughly 20 years ago. So we return here to classical image analysis, which can be strong, but certainly has some limitations. Now, there was one specific question about which type of images we can analyze. And to answer that question, I just placed here a selection of images that have effectively been used for analysis in Roxas. You see, it's a variety. It doesn't really matter much. What matters is rather that your target features, like the lumen in this case very often, is very distinct from all the rest that you don't want to measure. So we have seen that before. We have like the confocal microscope images, what Emanuela showed us. We also see a couple of bright field, thin sectioned samples. We see a surface scan with the oak and the chalk that was rubbed into the larger vessels. We see in the left corner, we see a fluorescence image. There you would say contrast is really poor. However, what is nice there is that the target feature is really black, truly black, and all the rest is a type of a bluish color. Now, in this question, in the full question, there was also the question about CT, which is a nice, let's say, link to what we have just heard. Roxas could also analyze, and also any other traditional image analysis tool could also analyze CT images, of course. However, only when they are, extracted in a 2D way. I think Jan also showed us that this is one of the applications. So this is absolutely possible. Important is the contrast to summarize, but also that the resolution of the target feature is sufficient, that you have a sufficient number of pixels representing your target features. So that was question one. And the second question was related to whether it is also possible to analyze decayed wood in the extreme case where there is only the middle lamella still present. Now, what you see here as a picture is showing more than the middle lamella. Still, this is what I could dig out. Thank you very much, Marina, for making this image. This is also old wood, relict wood that was buried in the sediments. And you see there is a degradation, and you realize where the problem is. The problem is obviously that the very fragile structures, they get disrupted. And partly because they are so fragile, they are no more in the right orientation, so they may actually turn down a little bit. And in the end, what you will measure here will not be very accurate. So technically it is possible, yes. However, very often the measurements will be very far away from what you would measure in a living tree. But maybe this is exactly the purpose of the person who asked this question. I don't know. Thank you very much for showing the slide. Now, well, we want to return again from this rather traditional image analysis to something that I personally also consider, in addition to CT, what we have seen before, as very promising. Please, Giulia.
Yes, so there were some very interesting questions about last advances in image analysis for quantitative wood anatomy, and also if there are any open or free software development for automatic feature recognition. So I think that stating what's the state of the art, to repeat myself, so what has been done by now is very important. And just 1 month ago, a very nice review came out about this. What I will not go into the review because, of course, it's a very thorough review and it states a lot. But the main goal or the main thing that I would like to point out is that this computer vision based techniques have been used basically on wood identification. So they have been focused on the wood species identification. So there is some kind of gap of knowledge, and there is one paper which is pointed out by the review as well about what is really quantitative wood anatomy or quantitative wood anatomical analysis. And this is a paper from Garcia Pedrero et al. And it deals with convolutional neural networks targeted especially to recognize cells. There is still room of improvement because this is focused just on one species, so Nothofagus pumilio. And of course, we would like to ease this process of quantitative wood analysis in all the steps. There is another paper which I found out recently from Yevchenak et al. But this is not really about the pictures themselves, but it's more about the analysis of the data, and they use machine learning approach where they state how what's the great potential of machine learning itself towards other classical approaches of course predicting what's the vessel lumen area of in this case corpus robur. Since I mentioned different and various techniques or approaches, I would like to give you a short introduction, a very quick, just to guide you within all this very fancy terminology. So deep learning is a subset of machine learning, which is a subset of artificial intelligence. Why are we specifically targeting deep learning? Well, it is very important, and it is of great use because it works exactly as a brain would work. So it can perform decision making. And what you need to perform decision making or decisions in general, you need a brain. And the brain is made of neurons or brain cells. These neurons are connected each other through neural networks. About quantitative wood anatomy, we specifically deal with convolutional neural networks because they perform very well on visual recognition tasks because the connection between these neurons are specifically targeted to this task, and they allow us to encode certain image properties. I would say that to answer the second question, it is important to point out the survey that we did roughly 2 months ago to tell everybody what are the advancements. So we use the QNet community to ask the other research group what it is going on regarding this new software developments for wood anatomical analysis. The results are this one. So we received 11 answers, and we can see how the main software goal is the wood anatomical measurements. And this is perfectly in line with what we just said. So there is a gap of knowledge towards this direction. species ID is the second one. So you can see it's a 45%. It's still very strong as an interest or as a goal. But of course, we need to fill this gap. I have to say that cell feature recognition is the last one, but it is strongly connected to wood anatomical measurements, because if you do not recognize properly with a certain accuracy cells and features, then you cannot have proper measurements. Another interesting thing is that gymnosperms and angiosperms are both targeted. So it is not like it is usually, so not just conifers, which are mainly used for quantitative wood anatomy, but the interest is broad and it is applied to both of these categories. We then wanted to ask how many of these 11 participants are using deep learning for this kind of new software development, and the result is 63%, so quite a lot. And 81% wants to go open source, apart from one person which didn't answer, and another result which was a freeware kind of software. So the open source possibility is there. We are going towards this. We are, as all QNet community and research groups in general, we are going towards that direction. The main programming languages are Python and R. And I wanted to point out this this last question that we made. So if people are working on standalone software or plugging for existing software. So basically people want to apply this software on a web-based browser, and somebody else wants to go for a standalone version. But yeah, mainly standalone and web browser based. R, of course, it's a plugin, so it would be within the plugin category. So what I wanted to say is that to answer this question, yes, we are definitely going towards the free software development direction, and the results are very welcoming because everybody agreed for a cooperation and collaboration within the research groups.
So thank you very much, Giulia, Georg, Tom, and Jan. Extremely interesting topic, and thank you very much for your nice presentation. We do have a burning question for, I think, Jan, is exactly how much will it take for the collection of one 3D image in a cube of 1 centimeter cubic? This is a very practical question.
Yes. Thank you, Angela, and thanks for the question. There is no single answer, like it takes 10 minutes or it takes 5 minutes. It depends on the resolution that you want to obtain. It depends on the quality that you want to obtain, and it depends on the features that you want to see. This can be scanned in 10 minutes easily, but probably you're not going to see the features that you want to see. It also depends on the kind of detector that you have available, the kind of geometry that you're scanning with. So there's different geometries you can scan. For instance, to give you an idea, if you have a 1 centimeter cube block, you could scan one half, you could scan the other half, and then you stitch together, which kind of could double your resolution. So yeah, but basically, for instance, with a standard, let's imagine a standard CT system, I think it would take approximately, to obtain a very good quality, let's say 30 minutes, and you get a resolution of 4 to 5 micron, maybe something like that, from the top of my head.
Okay, super. So could you give basically a range in between the worst quality and the best one that you can have? So in between.
Well, you can easily scan if you're only interested in, I don't know, in what kind of feature you might be interested. If you just want to use it as some kind of tomographical for anatomy, for instance, you want to have a quick view on the internal anatomy. Maybe you can do a very, very fast scan at 10 micron resolution, and then maybe in 5 to 10 minutes you could do your virtual slicing, and you could have a fast look at the data. If you want to have a more detailed higher signal to noise, for instance, typically then you need to take more projections, which makes that you need to take a longer CT scan. So then everything takes a little bit longer.
Thank you very much. We do have another question from Tim. Will be a follow-up widely used. Sorry, will be a follow-up of the software developers to see what the other are working on and how resources can be pooled and duplication of effort can be avoided. I think that, like, yeah. Maybe Giulia or Georg, you can answer on these questions. But I think that the QNet can really play a role here.
Giulia, I don't know, you performed the survey. You want to comment on this?
Yeah, so, well, follow-ups. Of course, this result will be available when this PDF will be put in the QNet community. Of course, we will work towards collaboration, and what is our aim is to give or to make this software available when it will be ready. So from my side, for what I'm working right now, it is not ready yet. It is working definitely, but yeah, we are waiting for publishing some results, let's say.
Good. Maybe then I add from my side as representing QNet, I fully agree with Angela that we probably should think about some sort of a meeting among all the 11 people who now gave feedback. I think that would be very interesting, but nothing is planned at this point.
There's the last burning question, and then I think
Angie is blocked in the screen.
Right.
Maybe I can ask the question instead of Angela. This is a very long question. It is from Satish Kumarchina, saying that in dendroclimatology, we require standardization, removal of non-climatic factor before further analysis. So the question is, do fiber dimension, tissue proportion, and ray parameters require same standardization technique for establishing any relationship with climate or any other factors? Try to answer this, but maybe this is more a question for the next stopover. So just if you want, you can answer, or we keep this question for the next stop.
I think we could keep it for the next stop. It's a very interesting question, actually. I haven't seen anything about, I mean, if it's aliform parenchyma, it will follow more or less the vessels, but still that's a whole other thing that not a lot has been said about that, I think. On the other vessels, there has been. So maybe that will be tackled in the next session. I don't know, Ute, if you could further elaborate maybe, but for parenchyma, at least from bit to bark.
No, I think we should do that in the next session, and also because it's time for the break. But we have one very short question to Jan. Maybe you can read it, Veronica.
Yes. So we keep this for later on. Probably it will be answered before the final burning questions. The last one is concerning the micro CT equipment to scan wood cores. Did you use a readily available scanner, for example, Phoenix Nanotom? This is very technical question.
Yes. Thanks for the question. No, we didn't. All the CT systems that we use are custom built at Kent University. But yeah, it doesn't mean that you cannot use any other system for these kind of scans. Not at all. Yeah, you can use other systems, readily available systems. Absolutely.